So today we're going to talk about JavaScript, and we're not just going to talk about JavaScript, we're going to talk about Rust powering JavaScript libraries and build tools. We're going to talk about the whys and the hows. We're going to talk about what tools are actually being built with Rust to target JavaScript engineers. And then we're going to cover how that's actually being done and how you can do it. But before we get started, I want to be very clear about something. This is about Rust and JavaScript. I'm not telling you to go rewrite everything you have in Rust. I'm telling you that in the right places, there are people making the decision to write Rust today to power tools that you already use, that you can make the same decision in some cases, and that Rust works well to power JavaScript experience. So don't go rewrite everything, but also don't be scared of it. Of course, the first thing we have to cover is why this is happening at all. And to do that, we kind of have to talk about Webpack. Webpack is pretty much the standard for build tooling these days. It's been a couple years, I'll say, of people trying to actively build projects to move away from Webpack. There have been alternatives like Rollup that target slightly different use cases in the past, but Webpack itself, while it was great when it came out in, 2014-ish, has gone through a number of major versions, and it would seem, if you pay attention to what's happening in the ecosystem, that Webpack is kind of at the end of its life cycle. It's still an okay tool, but there are creaks and strains, and people want better tooling. One of those people is the Webpack maintainer. So Vercel has this thing called turbopack, and turbopack they advertise very prominently as being a Rust-powered successor to Webpack that the creator of Webpack is actually working on. It's framed as an incremental bundler optimized for JavaScript and TypeScript written in Rust, which is, without the Rust part, vaguely what Webpack was. And why did they choose Rust? Well, they claim to be very fast as a result. And this is a claim that's going to get repeated over a number of different projects. I don't want you to take the speed claims too seriously. The things that I want to show and mention are, for example, Next.js 13 with turbopack is being compared to vite with SWC, which is also a Rust project. So we end up having the comparisons of, hey, we're improving our speed using Rust against other projects that are also using Rust. But Vercel isn't the only people trying to build a Webpack replacement. ByteDance has rspack. rspack is a fast Rust-based web bundler. Basically the same thing Webpack was, but written in Rust. So why does rspack work with Rust? Well, as you might have guessed, they also claim blazing fast. I don't know about you, but if I see blazing fast on another product page, I basically just ignore it. It's an extremely overused term in the JavaScript ecosystem. Here, the comparison is rspack and then Webpack again with SWC, another Rust project, with the stand-in default. So Webpack and Babel are kind of what's been the standard since 2014, 2015. It's been a number of years. And just like Webpack had tools built on top of it like Gatsby and Next.js and so on, rspack is also getting tools built on top of it. So there's rspress now, which is a static site generator built on top of rspack. And here I want to point out that they explicitly call out that it's simple, efficient, and easy to extend. So again, even though this project is very largely Rust forward, they are still claiming it's easy to extend. Earlier in this video, we talked a little bit about what Vercel was doing with turbopack, and they had a comparison against vite with SWC. Well, as it turns out, vite is going to go through not a full Rust rewrite, but they're going to adopt Rust for critical pieces of their infrastructure. The next 3 slides here I want to point out are from the State of Vite ViteConf 2023 presentation by Evan Yu. So if you're interested deeper in this specific piece, you can go find the slides. I'll link to them. But we talked about rollup earlier, and roll down is a Rust port of rollup. Roll down is still work in progress. It's early stage. It's not powering Vite today, but it's going to in the future. It's built on OXC, which is another Rust JavaScript parser project, and it's built in collaboration with the Rollup team. So there's a lot of inter-open source collaboration going on here to make this happen. And this is important because it's a huge language shift being done by a large group of JavaScript project maintainers. And I think Vite in particular is a project that wouldn't be using Rust if it didn't make sense. If they weren't going to be able to present the Vite experience the way they wanted to, they wouldn't be using Rust to power the project. And to that extent, Rolldown is going to expose a plugin container as an API. Vite is going to get a Rust core with Rolldown as a dependency. Performance critical pieces of Vite internally are are going to be Rustified, and there's a whole lot more to this presentation. So if you're interested in Evan Yu's talk, go check it out. That brings us to Parcel, another bundling tool that's pretty popular in the JavaScript ecosystem. Zero configuration build tool for the web, also starting to rewrite pieces of itself in Rust. Why is Parcel doing this? Well, just like everybody else, it's lightning fast. But what I want to point out here is Parcel's JavaScript compiler is built on SWC, same SWC that we've seen in the other examples. And Parcel builds quite a bit on top of SWC, things like the bundling itself, tree shaking, etc. The other thing I want to mention here is that Parcel's CSS transformer and minifier is built in Rust, but it's built in Rust on top of the same crates that are used to power CSS in Firefox. What this means is that they are using what they're calling a browser-grade CSS parser, which is the CSS parser that runs whenever you load a page in Firefox. This is really nice for a variety of reasons. One is that there's an industrial strength crate for doing the CSS parsing, which means that if something works in, say, Firefox or in a browser, you don't have to worry about a custom one-off parser not being able to handle it. It also means that these tools need to be very performant. If Firefox is slow because of the CSS parsing, people will use Firefox less. And by using Rust, you get to pull these crates into your project and take advantage of the work that's gone into them. Of course, we've mentioned SWC a few times now. It's used all over the place these days, and it's effectively a competitor to Babel. Again, SWC is claiming speed as one of its improvements, just like everybody else. OXC is the other JavaScript parser that's been mentioned. The JavaScript oxidation compiler is what they call it. And OXC claims, again, speed improvements. This time, not just speed improvements over Babel, but speed improvements over SWC. Lightning CSS is a tool for dealing with CSS that is partially associated with the Parcel project, but can also be used in many other projects. This is the project that's using that Firefox CSS parser. Lightning CSS, of course, also makes claims to being amazingly fast. And from having seen this AST developed over a period of time on the internet, I have to say that there has been a decent amount of work towards being a fast CSS solution. But again, the Lightning CSS website says Lightning CSS is written in Rust, using the CSS parser and selectors crates created by Mozilla and used by Firefox. Again, this goes back to the ability for these projects to use browser-grade crates to power custom tooling. Of course, that's not all. It's not just bundlers, it's not just CSS parsers, it's not just Babel competitors, it's also tools like Tailwind. Tailwind has merged a PR to make the Rust-based parser the default parser. As of the making of this video, I do not believe this version of Tailwind has been released, but it is coming. NX is a multi-package workspace tool that also has some Rust. Now, NX probably has one of the fewer uses of Rust compared to the other projects, but this is a video about using Rust where it makes sense, not rewriting everything in Rust. So this is actually a great example. So that brings us to why Rust, according to all of these JS tool marketing pages. And if you look at the reasons they give, it's fast, like we talked about. Parallelized architecture is another thing that they say, or browser grade tools. So is Rust fast? Well, sure, I guess, if you write a fast program. You know, like you can write slow code in any language. You can write fast code in any language. If you're doing performance work, the best thing to do is to not do the work, because not doing work or avoiding work that you don't need to do is faster than doing anything. And you can do nothing in all languages. So yes, Rust can be fast. It is not a language that forces speed on you. And it really, at the end of the day, does depend on what kind of approach you're taking with your program. Parallelized architectures was another thing from the JavaScript marketing pages. So what is that about? Well, there's a kernel of truth to this. If you want to iterate over a large collection of things, you can do that in Rust just like anything else, for loops, whatever, iterators. But Rust's ownership model in the borrow checker does lend it to making it easier to write code that is more easily parallelizable. So if you write code with Rust iterators, for example, there's a great crate called Rayon. Rayon will let you replace iter, which is a function for iterators in Rust, and you can replace that with pariter, which is a parallel iterator. And that's it. You've got parallelism. I'm not saying this is the solution to all your parallelism problems, but there is some truth to these claims that these JavaScript pages made. So the last one for JavaScript marketing pages, that Rust is somehow browser grade. And we did talk about this a little. It is true to some extent. If you use crates that are also used by Firefox to load pages, then that's about as close to browser grade as you're going to get. But thinking about it, there are other tools that use tools that are used in browsers. Node has V8. is that browser grade? So again, yes, there's a kernel of truth here, but also a little grain of salt. And are you not convinced by this list? I can't blame you. I'm not really either. These don't really feel like strong arguments. So why Rust? According to a different group of people, right? So not JS marketing pages, but people on the internet. Why do people who like using Rust currently use Rust? One of them is the type system. The type system is very expressive. It is integrated into the language in a way that TypeScript does not integrate with JavaScript. That is not to hate on TypeScript at all. It has a tough problem that it's trying to solve on a language that was not built with a type system in the first place, but that does have some drawbacks. Rust is a language that was built with types from the start and can take better advantage of that type system to give you amazing things like autocomplete that you like from languages like TypeScript. It's low level and it's high level. So you can go build an operating system, but you can also go build a web UI. And if you're building a web UI, you don't have to deal with pointers. It's much more like writing TypeScript than it is like writing. So you get that low level performance. You can get as granular as you need to write operating system level code, but you can also get as high level as you need to write not just web APIs, but also UI code. WASM is something that is connected to what I just said. So if you're writing UI code, you're probably compiling to WASM. And Rust, in my opinion, is the best ecosystem for writing WASM today. We'll get into things like the package manager and crates and the ecosystem and things like that, but Rust is very good at writing WASM. So if you have a reason to build WASM into your website, if you have a reason to build WASM into your application at all, Rust can be a great choice. Algebraic data types, this video is going on the internet, so some of you will know exactly what I mean when I say that, but the vast majority of you will not. These are very great, but you can just call them structs and enum. It's important that these carry data, but we'll get into that. It has no garbage collector, which means it embeds well. That means it can embed well in JavaScript, in Python, in Ruby, in Elixir. It can embed in the browser, in your JavaScript UI. It's not going to conflict with any garbage collector you already have running. It's fast and safe. And again, there's not much to say here. This is just kind of like very generic, but people say this kind of thing all the time. You saw it all in the marketing material. Oh, this is so fast. And then there's another group of people that is like, oh, this is so memory safe. But as JavaScript developers, you already work in a memory safe language, so it doesn't mean a lot. The error handling is quite good in Rust. Errors in Rust tend to be values, so you tend to be able to deal with them on a per error basis. And the error reporting is getting better every with awesome crates like anyhow, color air, and yet. Cargo is Rust's package manager. People really like it. Rust had what I will say is the advantage of time in that it got built after all of these other languages. So it got to take insight from Ruby's bundler and JavaScript's NPM and Yarn and all of the other package managers that existed. Cargo is somewhat the result of having seen all of those ecosystems. It's got testing built in. It's got benchmarking built in. It's got documentation built in. We'll talk about that more later, but it's an amazing tool and it's got so much built in that you need. Rust Analyzer is something people really like. It's what powers all of the great autocomplete in your editor. And because the type system exists in such a way that it does in Rust, this means that you get access to very high signal editor autocomplete. There are functions associated with types that you can call, and those functions are very often the ones that you can call. They are not text matches. They are not pulling from some dictionary database. These are actual functions that are defined to be associated with the types that you have and the values that are in your program. Scoped resource management is actually really nice. This is the kind of thing where if you open a file, you also kind of have to remember to close the file. In Rust, this is often handled via the drop trait. So you can open a file in some function, and at the end of the function, Rust will call drop for you, closing the file. Zero cost abstractions come up quite a bit, and this is kind of a foreign concept for JavaScript people, but the idea here is that if you use a high level language feature, right? If you use generics or something like that, that will add a potential compile time cost, but it will not add a runtime cost. So you get to use nice high level language features, and you only pay that cost when you're compiling, not when it matters when you're running your production application. Pattern matching is huge. I love pattern matching in basically every language. I think JavaScript is supposed to get this soon. We'll talk about this a little bit more later. The type inference in Rust is really, really, really good. You have to put type signatures on all of your functions for the arguments and the return values, but everything inside of your function, for the vast majority of cases, can be inferred. This is really nice because you don't have to put a lot of extra annotations on things that don't actually need them. You are obviously always welcome to put as much type annotation as you need for it to make sense for your program, but Rust type inference is very strong The compiler error messages we're going to cover in a little bit, but they are very good and people put a lot of work into making them good. The most high praise that I can give the Rust compiler error messages are that they are worth reading. Again, Cargo has built-in testing, built-in formatting, built-in linting. This all comes with the package. You know, it comes as part of the Rust package. So that leaves us with fearless concurrency, refactoring, etc., and memory safety. I'm not going to talk about memory safety because JavaScript developers already work in a memory safe language, and it really doesn't mean a lot to you. Memory safety is a concept that's kind of used to sell Rust to C developers. But fearless concurrency and the refactoring that you can do with Rust are huge selling points. The way the memory model works, the way the borrow checker works, the way the ownership model works, the way Rust Analyzer will support you as you try to refactor your program. Rust is not unique in being able to refactor well, but I will say that Rust refactors very well. So with all of that said, all of the JavaScript marketing material, all of the people on the internet, why Rust? And in my opinion, it's not because Rust is amazing. It's because Rust can enable you to be amazing. So there's this concept of fire flowers, which is basically like the idea of you get a fire flower in Mario, and now Mario is a superpowered Mario that can shoot fire flowers. So what does Rust enable you to do? It enables you to write programs in wide areas of applicability. So like we said before, you can write operating systems, embedded software, networking, you can do web APIs, you can do CLI tools, and you can do web UI. And there's not a lot of languages that can span that whole width. We mentioned it earlier, but the testing is built in, the documentation built in, and there's some modern package management. Having testing built in, I have to say, means that I write far more tests than I used to. Tests are pretty much always good to write, but having the capability to write a test in the file that I'm working in the source code with, and then just run cargo test, has led to me building so many more tests and giving me such a higher level of confidence in my code. Documentation is also built in. You can do a cargo doc, and that doesn't just mean that you're getting like type docs, you know, those people who are like, oh yeah, types are documentation, we don't need to write any. That's not what this means. This means that you can write full-on markdown prose inside of your Rust source files, and that will get documented when you run cargo doc and send your library somewhere. This also means that any documentation that contains examples and example code will also get compiled. That documentation example for that library that you're trying to use that was out of date 3 years ago because nobody remembered to update it, you can avoid that in Rust by using compiled documentation examples. Modern package management, again, Rust really has the benefit of being built after a whole bunch of other things and being able to learn from them. So Cargo learns a lot from all of the other ecosystems. Rust allows you to build maintainable programs. I've spoken about this on my channel before, but the idea that you can write some code and it will still compile next month or 3 months from now, even if you don't touch it, or that you can come back to it and start refactoring and not have to worry about too much. You can let the compiler kind of guide you and tell you what things need to be changed if you say change a data structure, right? So the idea that you can write code that targets some regular generic data structure like a vec, and then later find out that you need to change that vec to something a little bit more optimized because it doesn't quite fit your access patterns for your program. Rust makes swapping that out and figuring out all the places you need to change things very easy. Relating to that, Rust has performance that sticks. And what I mean by performance that sticks is that you can make changes to your Rust program. Let's say you wrote with a bunch of allocation, you remove all that allocation, you use references, do a bunch of pre-allocated data structures. The data structures that you put shared references into the types of are very obviously shared references. They are not just going to go magically back to an allocated version when somebody makes a PR, right? So you don't get much spooky action at a distance when you're dealing with performance, which is really nice. And again, it embeds well in other languages. This can be seen very obviously in ecosystems like Python, where Rust is being used to power data frame libraries. But this means that Rust can be an addition to wherever you're working. So this is a video about JavaScript. Rust embeds very well inside of JavaScript to superpower the things that you're building in JavaScript when you need it to. You don't need to rebuild everything in Rust to see the benefits of Rust. The error messages, again, my highest praise for those is that they're worth the time to read. I can't say that about every error message that I've ever read. And the editor support is fantastic. So Rust Analyzer is a really solid tool and can write a lot of code for you. It can show you all of the types in your program because Rust type system is great, the inference is great, and Rust Analyzer can show you all of that. And in general, I think it's fair to say that Rust helps you build better programs and empowers you to do so. And that's why I would suggest using Rust. This is a quote from somebody that works on Rust. Specifically, this is in relation to working on the error messages that come out of the compiler. And it's diagnostics should always be clear on what the problem is. And when they don't, that's a bug. So what this is saying is if the Rust compiler outputs an error message that doesn't tell you what's actually wrong with your program, the Rust team will consider that a bug that you can file an issue against, and somebody will work on fixing it. This to me is huge and is a large reason as to why the compiler messages in Rust is so good. So that brings us to how do you actually do Rust and JavaScript? How do you embed Rust in JavaScript? How do you use Rust with JavaScript? And the answer in this video is going to be 3 ways. One is going to be write Rust, embed in a JavaScript package. The second is that you can publish Rust binaries to NPM if you want to. And the third is compiling Rust to WASM. So embedding Rust. Rust has no garbage collector. We talked about this earlier. No garbage collector means it embeds really well. NAPI RS is the trait that we're going to look at for building native modules in Rust, compiling those to something that can run, say, inside of Node, and expose JavaScript APIs. Again, Rust does this very well, so you can get this in Python and Ruby, Elixir, JavaScript, etc. There is some maintenance downside. You do end up with N+1 packages. So you end up with the library that you're using to expose to users, and you end up with an additional package per platform. Because again, Rust is a compiled language. You do need the package that you compiled for a particular architecture. This isn't a big deal for your users. They won't even notice. But from the maintenance side, you have to build Rust for, say, an M1 differently than you build Rust for Linux. Rust can do 0 copy over the JavaScript Rust boundary. If you know what that means, then you know what this means. And if you don't, consider it a performance benefit. And also really important is you're not using some like arbitrarily small subset of Rust to do this. You can use fully async Rust and a bunch of other regular features. So this is what it looks like to write an NAPI library. On the top, we've got a .rs Rust file. We're bringing NAPI into scope. This is basically an import at the top of the file. We use something called an attribute macro. So hash bracket NAPI is going to write some code for us. It'll generate the code that is required to do the binding of this function. Because again, at the bottom, we're going to call this function from JavaScript, but writing the code to like glue those two things together is super boring and very repetitive. So we just let the macro write it for us. I'm sure none of you care about Fibonacci, so the implementation of this function isn't really important. I just needed something short enough to show you. But Fibonacci takes some number and returns some number. U32, if you're not aware, is a 32-bit unsigned integer. That means it's a positive number that is an integer that can be from 0 to something that is fairly large. And on the bottom, you can import this Fibonacci function from this file like it's a normal JavaScript package and then use it like it's a normal JavaScript function. Where users do not have to know that you wrote this library using Rust. This is what the package setup looks like for NAPI. On the left-hand side, you have an example. In this case, we're using something that is node.rs/bcrypt, some theoretical package. Your dependencies go in optional dependencies, which then get downloaded on the relevant platforms. And on the right-hand side, we have all of those platforms specified with an OS and a CPU architecture so that they get downloaded on the right platforms. Again, this package setup is mostly a maintenance burden. It is not a runtime burden. It's not an end user burden. So your users won't know and they won't have to care. So option 2, you can publish Rust binaries to NPM. It seems really simple at first. There's a bin path in package.json. If you point that to a path, then that binary should be copied into, node modules.bin, whatever. It turns out it's not that simple, but it's still doable. So if it's not that simple, what are your options? Well, you can manage the binary download yourself. There are libraries to do this. One of them is called binary install. It's at the link right here. You can write this code yourself. It is not that much code. Your other option is to do exactly what we were just doing with NAPI. Publish multiple optional packages, which has a slightly higher maintenance cost, but this can all be automated and it's not that big of a deal. Option 3, compile Rust to WASM. The browser can run WASM, Node can run WASM, other ecosystems can run WASM, WASM all the things. Compiling to WASM is not hard. It is more or less built into the Rust compiler. So if we cargo build, specify the WASM32 unknown target, then we get a WASM file instead of a binary file that you can run on Linux. Depending on what you're doing, there's obviously a lot of variations, flags, and whatever that you can optionally set. This is the basics. WASM bindgen is how you bind to JavaScript functions in WASM. So if you were going to call the alert function from the window in the browser, WASM bindgen would be how you bind your Rust code to be able to do that. It is also how you would expose a function from WASM to be called from JavaScript. And obviously on the web, we care a lot about the size of the things that we're sending over the wire. I don't have the numbers in this video specifically, but the last numbers that I saw was something roughly like you can download and parse and compile about 2x the amount of WASM compared to the same amount of JavaScript. WASM opt then is an optimizing compiler that you can run on the WASM file that comes out of cargo build, which will make it even smaller. There's additional tools called trunk that we're not going to talk about today. Suffice it to say that Rust has a rich ecosystem for developing WASM applications. WebSys is the package that already contains all of the bindings to all of the browser APIs. So if you're looking for that alert function like we were talking about earlier, that already exists in WebSys. You do not have to bind it yourself. And then we're not going to talk about it today, but Rust is so good at compiling to WASM that there are full stack Rust web frameworks that you can compile to WASM and go deploy on an edge platform like Dino Deploy. In this case, I'm specifically talking about Leptos. That's for another day. This is WASM bindgen in practice. This is raw WASM bindgen. This is as if you're not using any of the other crates or anything like that. So even though we have access to WebSys, which would have this alert binding, this is how you would bind it yourself. Basically, you define an external, you define what the function is, the arguments it accepts, and you use the WASM bindgen macro to generate the glue code. Same thing for functions that are defined inside of Rust that you want to expose. In this case, we've got a greet function. We've got WASM bindgen on top of it. It takes an argument of a string. It uses the alert function that we just bound to above and greets you with hello name, which is the argument we passed in. Again, this looks very much in the JavaScript file like it doesn't even know the WASM exists, right? Import greet from hello world, call greet hello world, and everything runs. Now, when you're using WASM bindgen, you do tend to compile for specific platforms. If you intend to use something inside of Node, you would compile with a Node target. If you're going to use it on the web, you would compile with a web target, and so on. After doing the cargo build, this is what the target looks like. So WASM bindgen, we create an out directory, which is where all of our files are going to go. You choose your target. In this case, we're going to run this on the web. And then we grab that WASM file from our previous cargo build. If we look at the output directory, a JavaScript file that will load the WASM file, we get a TypeScript definitions file for both our JavaScript file and for the WASM. And of course, we get the WASM. Now, this is the default. So I got a size of about 26 kilobytes. I have done 0 performance optimization, 0 size optimization. This is just what you get by default if you do nothing but build. But you can bring that down. That can come down to about 12.6 kilobytes. This is about the lowest you're going to get. 10 kilobytes of this are what's called an allocator. If you really care, you can go full no standard and you can drop the allocator and drop that 10 kilobytes. But most people aren't going to be working in that environment. But what we do have is tools that are very similar to something like Webpack Analyzer if you've used that. In this case, I'm looking at a CLI tool called Twiggy that will show me what's in my WASM bundle. In this case, DLM alloc is the allocator that I talked about. So whenever you're looking at the percentage on the left, anything that's labeled as DLM alloc on the right would get removed if we've removed the allocator. And you can see our greet function down there. It's 1.4% of our program. So now maybe you're convinced that you would like to learn a little bit of Rust. This is going to be a super high level, sky level overview of Rust designed to make you just not scared of it, basically. If you have concerns about maybe needing to write pointers or manually manage memory or something, this section is here to assuage all of those fears and to basically tell you that you don't have to do that. So we've got Rust on the left, JavaScript on the right. If you've worked with JavaScript, you know that npm, Volta, N, FNM, etc. We've got tons of options for version managers. We've only got one option in Rust. It's Rust up. For all of the other things that you do in JavaScript, whether that's package management with npm, pnpm, yarn, other new tools, testing with Jest, vtest, or the new node test in Node, building with Webpack, Turbo, or any of the other tools that we talked about, type checking documentation, extra linting, formatting your code automatically. All of that is kind of built into Cargo, and you can compare that against your favorite JavaScript tool for doing the same. The one thing here that I will point out specifically is that cargo toml is basically our package JSON in Rust land. That's where all of our dependencies would go, and so on and so forth. You can, of course, if this isn't enough, extend cargo. So you can run cargo install cargo-watch. Cargo-watch is a crate up on crates.io, our package registry, and that gives you access to the command cargo watch now. So you can cargo watch -x build, and every time the files change in your project, it'll build. Wonderful. Similar tools to this exist for Lambda, which is for testing, building, cross-compiling, invoking AWS Lambdas. There's Cargo Flamegraph for flame graphs. There's ESP Flash for ESP32 devices. Cargo Dist and Cargo Released are release automation, not just for getting a crate to crates.io, but also getting it to Homebrew or GitHub releases or any number of other places. Cargo Insta is a crate that does snapshot testing. Cargo Insta is a CLI tool to manage those snapshot tests. Cargo Next Test is if you end up having so many tests that it becomes an issue for you, well, you could move to Cargo Next Test. So let's take a high-level look at the language itself. This is a hello world for Rust. It uses some new syntax. So right up at the top, we've got shebangs. On the right-hand side, we've got hello world JS. On the left-hand side, we've got hello world RS. The shebang defines what program we're going to run when we execute this file. In the output.text on the bottom, you can see /hello world.rs. This shebang at the top is what allows us to do that. Now, if you use Node and you're watching this video, you've probably never used a nightly release version of Node. In Cargo, using a nightly release version or any other version is really easy. You do cargo plus nightly or plus any other release, and then whatever command you want to run. In this case, we're using the script command, which requires that we use nightly, which is why we're using nightly. That should stabilize sometime soon. I don't know when. It's not terribly important though. So on the left-hand side, we've got function main, and then we've got a macro print line with the word hello. Print line is basically analogous to console log. It allows us to do some additional stuff, but there are multiple kinds of macros in Rust. This one is a function-like macro, so we call it like a function. Earlier in this video, we saw attribute macros, and there are some others. We're going to skim really quickly over variables. In JavaScript, we've got const, let, and var. In Rust, we have just let and let mute. Let is an immutable binding, while let mute is a mutable. So if we do let x equals 5 and we do let mute y equals 5 and debug them out, on the right hand side here, you can see we've got x equals 5 and y equals 5. If we set y equals to 10 and we debug them out again, we get x equals 5 and y equals 10. It worked. The only other thing I want to mention here before we move on is the debug macro, dbg, gives some really useful output. So on the right-hand side, it gives you the file name, the line location, the expression that you gave it. So in this case, that is variables, rs is the file, line number 8, the expression is x, which is just a variable, and then the value that expression evaluates to. So in this case, that's just 5. So on line 11, if we uncomment that line and we try to set x equal to 10 and we run our program, we get an error message. And I want to point out that this is one of the error messages that is useful to read. In this case, we get cannot assign twice to a mutable variable x. We get an error code that we can go look up on the internet if we want to. We get the file name, the line number, the column number, typical stuff. Now, I will point out that we only have the code that matters. So we have the code on line 5, which is let x equals 5, and we have the code on line 11, which is where we try to reassign x to 10. The red error message says we can't assign twice to an immutable variable, which is true because we did let x equals 5. The blue text is kind of like help text. It's saying, hey, this is your first assignment to 5. This is where you first defined it. And some help text that says, hey, consider making this binding mutable. And if you see that example that they give, it is exactly what we did to make y mutable. So it's the right thing to do. So if we did let mute x equals 5, this error would go away. Here's a brief intro to structs. There's one more type of macro that we didn't talk about, and that's derive macros. Like we talked about earlier, writing code that is repetitive and boring is not fun. So that's why we have macros in Rust. In this case, we're deriving an implementation of debug because on line 14, we use the dbg macro, and that calls out to the debug implementation for whatever type we have. Not super important, just doing some code gen for us. So we have a person struct that is roughly equivalent to a typed object. We've got a name that's a string and a height that's a U32. In this case, it's my name, Chris, and my height, 206 centimeters, and then we debug that out. In JavaScript, the result we get is just the object. In Rust, we get a lot more output. And we get a lot more output because Rust already knows that we aren't using the fields in this struct. So we've defined this person struct. We've instantiated this person struct, but we never use the field. We never access name and we never access height. Other than that, right at the bottom, it says structs rs 14 person, which is the expression, and then the struct person. That brings us to enums. Enums are the second thing when I mentioned, algebraic data types earlier, structs and enums. In this case, we've got an enum of fruit with variants apple, pear, and banana. We instantiate fruit apple and we debug it out. On the right-hand side, this is roughly equivalent to the same JavaScript. And if we run the JavaScript code, we get symbol apple. If we run the Rust code, again, we get significantly more output, but that's because Rust knows that we used apple, but we didn't use pear and we didn't use banana. So Rust, to some extent, knows when you're using pieces of code and when you're not. You are getting dead code elimination already. You do not have to configure it. You do not really have to worry about losing it. And when dealing with enums, we can use Rust Analyzer. So this is inside of VS Code here. We're writing a match expression on my fruit, and we're using Rust Analyzer to write this code for us. I click fill match arms, and we get all of the variants matched against and to-do macros in the locations that we need to write code. So if we pull this into an executable file and we run, right at the bottom here, it says not yet implemented. That's the to-do macro. The to-do macros are really nice because you can also pass in some string of text. To do, apples are for later. We're going to do it later. The to-do macro will panic your program and crash it with this message, but only if you hit that at runtime. So it will interfere with type inference, right? So we don't need to return anything here. We don't need to write out scaffolding code. We can just say to do, and the Rust compiler is going to be like, hey, if we run into this, we'll stop running because you're supposed to write this code later. But if we don't run into this, then the rest of the program will operate as normal. And if we include that string in the to-do macro, we get not yet implemented, apples are for later. Enums, very importantly, can also hold data. If you've ever used something like Redux or written a reducer, you might recognize this pattern. Instead of having a type field on all of our JavaScript action objects, along with a payload, we can have an enum called action with a bunch of variants. So in this case, we've got an add to do variant that's written much like a regular struct would be. The remove to do and complete to do variants, which hold only one value. So it's a type of I32, which is a signed 32-bit integer. We can construct an add to do just like we would any other struct. And we can match on that action and destructure the fields out of those variants to do whatever we want in these branch arms. And when we run this, again, Rust knows that we didn't use the IDs. So if we wanted to, we could put an underscore before the IDs and silence these warnings, but it also knows that remove to do and complete to do weren't even constructed. There are many built-in enums, such as option, in the Rust standard library and used across the ecosystem. I wanted to emphasize that you can build your own first, and that option and other enums like it are not special. In this case, on the bottom right, we've got the definition of what an option is. It's just an enum with two variants, one of which is none and one of which is some that contains some type. It's useful to mention at this point that Rust doesn't have undefined or null. So if we want to represent data that can be missing, we need to use an enum like this. So in maybe something on the left-hand side, we construct sum 200. So this is an option type where that T type is, an I32. We match on maybe something. If it's some number, then we debug that number and we return it. If it's none, then we default to 0. It's useful to mention here that Rust is an expression-based language, and that means that the match expression returns a value. In this case, that value is going to be at either one of these branches, so either the sum branch or the none branch, and that will either be line 9, which is the last expression in the sum branch, or line 11, which is the last expression in the none branch. In either way, our number will be some number, and we can debug that out. It's either going to be 0 or whatever number we gave it. There's a simpler way to write this though, as there often is in Rust. All of these types, like option, have a bunch of functions defined associated with them. In this case, we have a function called unwrap or that does basically exactly what we just saw. If there's an integer inside of this option, if the variant sum value is in there, then unwrap that and give us the integer. Otherwise, use the integer 0. And this is the exact same thing. Iterators are a really important concept in Rust because they appear all over the place. They are what powers the for syntax, but they also power really powerful things like collect. So in this case, we're looping over the numbers 0 to 10. If you've never seen a range, this is a range. This range will give us the number 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, stopping before 10. We debug that out. So on the right-hand side, you can see all of those numbers for each number in the loop, but iterators are also more powerful than that. We don't just have to use them in for loops. On line 5, we define a range of characters. This is notably different than strings because characters are single characters. So in this case, we are defining a range from A to Z, lowercase, and we're using .collect to collect all of that into a string. So we get the alphabet as a full string. Now, collect is super generic, so we do have to tell it what we want it to collect into because it can collect into many, many different things. Now, it's often said that these ranges and structs and values and whatever are iterators, but what does that mean? It means that they implement the iterator trait. Traits, if you're unfamiliar with Rust, you can basically call interfaces. So there's this iterator trait. It's got an item type associated with it. This item type is going to be whatever we're iterating over. In the first example, that was an i32. In the second example, that was characters. The only function that is required to be defined here is the next function. Everything else can be implemented in terms of next. And you'll see that next gives us an option self item. So if we call next enough, eventually there are no items left in the iterator and it returns none. And that's how we know we're done. And of course, going by what we just said, there has to be an implementation of this iterator trait for ranges. And in fact, there is. So if we take our newfound knowledge and we say that a range from 0 to 10 implements iterator, that means that we can call .next on that range repeatedly, which will return us an option that we can unwrap because we know it's going to be there. And we can just debug that number out. So we can keep calling next and keep calling next and keep calling next and debug that value out and debug that value out. And it just keeps giving us the next one. This is what's happening under the hood when you use a for loop. So if we go back quickly and look at the for loop, this for loop is just calling next automatically until that iterator returns none, and then it's not iterating anymore and it moves on with our program. In the same way, collect is just calling next for us under the hood. And whenever next returns none, it stops and wraps everything up into this string and returns it for us. I mentioned testing and how it's built in. In this case, we've got a library that we're building, this super complicated add function that takes two usizes and adds them together. A usize, if you're unfamiliar, is a platform dependent unsigned integer. Usually that means it's a U64, but it can be a U32 or something else. It depends on what computer you're running your program on. The config macro allows us to only compile this module. So mod tests is like having another file, more or less, in JavaScript. Modules and submodules in Rust aren't tied to the file system. So we can create this tests module. We can say only compile this when the test flag is true, bring in any functions that we defined in the parent module. So superstar is anything in the parent module, which happens to be in the same file. And we can use the test attribute macro on a regular function. And if this function panics, our test will fail. If it doesn't panic, our test will pass. So if we run cargo test, it will run our tests. It runs our unit tests, and you can see it's actually running our doc tests here, even though we don't have any. And our test passed. Wonderful. Async also exists in Rust. The biggest syntactic difference is that await is after the expression rather than before. In JavaScript, we await something. In Rust, we call something that returns effectively what is a promise. It's called a future in Rust. And then we await that. The postfix await is actually really nice. I have grown to prefer it over the JavaScript version. It allows you to chain async expressions together. So if we had another and then we awaited that and it returned something that we needed to await again, we could just keep doing that. But in this case, we've got async function main. Main is the function that we have to define for any binary. And we've got some async function another that takes a number, adds 5 to it, and returns it. Now, the biggest difference here in terms of how async functions is that the runtime comes from a third-party crate. In this case, it's coming from Tokio, and Tokio provides us with this Tokio main macro that will write some code for us. So this Tokio main macro will take the async off the front of our main function and start the Tokio runtime, which will then make sure that all of our futures are pulled appropriately and whatnot, allowing us to use this async syntax. If it sounds a little bit more confusing than JavaScript's version, it's for a good reason. And that reason is because Tokio is a production grade web server level kind of async runtime. Doesn't need to be the one we use. We can also use an async runtime on embedded systems. There's a crate called Embassy that does this. So you can make different trade-offs for how you want to write your async code based on which runtime you want to use. And this is actually really nice. If we want to see what the Tokio main macro is actually doing for us, Rust Analyzer again can just tell us. If we expand the macro recursively, it opens up a pane with the expansion, and the code we wrote on the left directly compiled to the code on the right. So in this case, we've got a main function, an async block with the code that we defined in our main function, a couple of clippy lints that we won't talk about, and then the Tokio runtime that builds a new runtime enables some things, builds it, expects it to work, and then runs our code. The point here is not that you perfectly understand what's going on the right-hand side. It's that macros are not magical, and you can directly see the code that they compile to if you want to. And getting to the end here, here's our one slide on borrowing. So we've got this dog struct that has a coat color that has a string. So in our main function, we have a dog with a white coat color. We've got 3 functions here defined on the right: pet dog, die coat, and someone adopts dog. Each of them takes a different kind of argument, even though they're all dogs. Pet dog takes a shared reference to a dog and then uses that shared reference to debug the coat color out to the console. What this is doing is it's basically saying, hey, you can pet the dog, but when you're done petting the dog, I'm going to take it back. While you're petting it, you can't change anything about the dog. You can't change the color of its coat. You can't cut its hair. You can't adopt it. You can't do anything with it, but you can look at it. That's why it's a shared reference. Die coat takes an exclusive reference, or something people sometimes call a mutable reference. An exclusive reference means that I'm going to give you the dog. Maybe you're giving the dog to the groomer, for example. The groomer then, because Halloween is going to come up soon, dyes your dog's coat orange. They can do that because they have an exclusive reference. Once they're done, they'll give it back to you and we have the dog once again. So in our main function on line 13, we get the dog back. But maybe that orange coat color really sings to somebody and they decide they want to adopt the dog. Well, if somebody adopts the dog, we are giving up ownership of the dog. The dog is then moved into this function, and this function owns the dog now. It doesn't come back. There is no reference here. That's why it's not coming back. So the dog gets adopted and goes away, and that means we can't pet the dog anymore, because in the main function, someone adopted it, we gave ownership away, and now it's not there anymore. We can't use it. So if we run this program as is, you get the output you might expect. You get the coat color is white, the dog then gets adopted, and at the end, the dog has a coat color of orange. But if we uncomment that code on line 16 and we try to pet the dog, after we've given it away, after we've given up ownership, we do get a compiler error message. And this is one of the compiler error messages that you will see when you start writing Rust, if you start writing Rust. A borrow of moved value dog. So our variable dog owns the value that we created with the dog struct. On line 14, the value was moved into the someone adopts dog function. And on line 16, we are trying to borrow the dog again after moving it, but it's not around anymore. Now, the Rust compiler helpfully tries to say, hey, you could change this if owning isn't necessary, but adopting is kind of an ownership centric thing, right? If somebody adopts a dog, they get to take the dog home. It doesn't stick around forever. But it does tell us that this parameter takes ownership of the value in this function. So that's your one pager on borrowing. Again, it's more about sharing references or giving away ownership. You can also choose other approaches like making copies, although that doesn't really cleanly map to the dog analogy unless you're a mad scientist, unfortunately. But making copies of data and passing that into other functions is a totally valid approach. And then you just have 2 copies, one of which still lives in the main function and one of which can go with the person who adopted the dog. So to close up here, how is Rust useful? You can build standalone build tools. You can embed it natively in NPM packages and expose JavaScript APIs. You can use Wasm in the browser or Node doing the same thing. You can build serverless functions and other tools like that, or you can use it to build sort of industrial strength tools. So like WGPU is the web GPU implementation inside of Firefox. It is a crate that you can just pull into your project and start using. If you want to build the next Figma, WGPU could be a good option for you to start with. And finally, what is Rust? This comes from rustlang.org. It's a language empowering everyone to build reliable and efficient software. And that is really the selling pitch that I believe in. If you are going to use Rust, it is going to be because it enables you to do things that you either weren't able to before or had a harder time doing before. It is not going to be because somebody told you Rust was memory safe. So that's it for today. I hope you enjoyed the video. If you have any questions, leave them in the comments and I will catch you in the next one. Have a great rest of your day.